is the transfer function of a feedback control system is given, and that is T of s equal 50k by s power 4 plus 20s cube plus 15s square plus 2s plus k. Now he is asking find the range of k such that the system is stable. Now a system is described by a transfer function that is given in the problem. Now he is asking whether the system is stable or not, and find the value of the k such that the system is stable. Now we have to find out the value of k such that the system is stable. That means here it is a conditionally stable system. So that means if the condition is true, then only the system is stable, otherwise the system is not stable. So that's why we have to find out the condition for system stability here, right? So to find out the system stability, first we have to find out the transfer function, right? The transfer function is directly given here, so that's why our work is simplified. So here, and next, after finding the transfer function, we have to find out the characteristic equation of a system. Now what is the characteristic equation? If you find out the transfer function, the denominator part is nothing but a characteristic equation. Here the denominator is s power 4 plus 20s cube plus 15s square plus 2s plus k. This is equal to 0. Now this is our characteristic equation. After finding the characteristic equation, then the next step is we have to find out the Routh-Hurwitz criterion. In the Routh-Hurwitz criterion, we have to find out a table. Now the table indicates s power 4, s cube, s square, and s power 1 and s power 0. Right, here the s power 4 means 1 multiplication factor, and then we have to look for s square. S square multiplication is 15, and then s power 0. S power 0 multiplication factor is k. Right, after that s cube multiplication factor, that is 20, and then s multiplication factor, that is 2. Now then we have to find out all these rows, and after that we have to decide the system stability condition. Now this will be 30 minus 2 by 20. 30 minus 2 by 20, because 20 15 is 300, sorry, 300 minus 2 by 20. Now this will be k, and after finding that we have to find out s power 1 coefficient, and s power 1 coefficient is this 300 minus 2 by 20, and this will be 14.9. and after that we have to find out s power 1 coefficient. So here we have to fill up this row. So this row is 14.9 multiplied by 2 minus k by minus 20k, sorry, by 14.9. Now this coefficient will be 0, and again this coefficient is k. Now to decide the system stable or not, here, okay, for deciding that, if you observe the first column of the Routh-Hurwitz criterion, that should be all positive coefficient. If you get the positive coefficient, then the system will be stable. Now 1, this is a positive, and 20, this is also positive. Now here 14.9, this is also positive, and if you come to s power 1, here the 14.9 into 2 minus 20k, this should be positive. This should be positive means what? The 14.9 into 2 minus 20k should be greater than 0, then only this is positive, and s power 0 coefficient is k, so this is also positive. That means what? K should be greater than 0. Now these are the two conditions. If you satisfy these two conditions, then we say that the system is stable. Now find out the condition here, right? If you solve for this, we will get k equal 14.9 into 2 by 20. So that means we will get 1.49. So that means if k is less than 1.49, then the system is stable. So the marginal value of the k marginal value is 1.49 that we got. Now if the k is less than 1.49, the system is stable. And also one more condition is there. If k is greater than 0, then the system is stable. If you couple these two conditions, and our option will be D, 0 less than k less than 1.49. Question is, the transfer function of a feedback control system is given, and we have to find out the frequency of oscillations such that the system is marginally stable, right? So if the system is marginally stable, that means it will be, the roots are at imaginary axis, so that's why it will have some oscillations. Now we have to find out that frequency of oscillations. Right, for finding that, first we have to know the transfer function. Right, directly he is given the transfer function. Then we have to find out the characteristic equation. The characteristic equation is nothing but the denominator of a transfer function, and the denominator of a transfer function is s power 4 plus 20s cube plus 15s square plus 2s plus k. This is the denominator of a transfer function, and it is also called characteristic equation. After finding that, then we have to find out the k marginal value. At k marginal value, then we have to look for the characteristic equation, and that means we have to look for auxiliary equation. Then auxiliary equation is the here second order equation, and after that we have to replace the k marginal value there. Then we have to find out the frequency of oscillation. So first, before going to that, first we have to find out the k marginal value. K marginal value we can find with the help of Routh-Hurwitz criteria. Right, here Routh-Hurwitz criteria, I am forming here the table for Routh-Hurwitz criteria. Right, if you solve this, I got the k marginal value as 1.49. Here, how to find the k marginal value? At that point, the system is in the conditional stable. After that point, the system is unstable, and before that point, the system is stable. And that is the marginal value above which the system is unstable and below which the system is stable. And that point is known as the k marginal value. Under k marginal value, all the roots of the equation, all the roots of the system is at imaginary axis. That means the closed loop poles, or I can say the closed loop poles of a system is at imaginary axis. So we have to find out that point. That point is k marginal, and the k marginal value we got 1.49. After getting the k marginal value, we have to find out the characteristic auxiliary equation. And the auxiliary equation is this equation is the auxiliary equation. Right. So here the multiplication of s square factor is 14 point. The multiplication of, I am writing here, the multiplication of s square factor is 14.9 into s square, and plus k, where k is, I got 1.49, and this is equal to 0. If you solve this, we'll get, because s square is nothing but minus, and s equal to j omega. If you substitute here, minus omega square, that means 14 minus 14.9 omega square equal to minus 1.49. So from this, what we'll get is omega square equal to 1.49 by 14.9. So with this, omega equal to under root of 1 by 10, and this value is approximately 316 radians per second, 0.316 radians per second. So that's why we have to go for option C. Option C is 0.316 radian per second.